One and all. This particular seminar is organized by Seminar Committee of KFRA. On behalf of Seminar Committee, I welcome you all on this occasion. And the world is celebrating Meteorological Day to spread awareness about the behavior of the Earth atmosphere and our role in protecting it. World Meteorological Day marks the foundational anniversary of the World Meteorological Organization, and WMO was founded 7 decades ago and lists weather, climate, water, and environment as their primary concern. World Meteorological Day 2022 holds special significance as it is dedicated to raising awareness about the environmental condition of our planet. Since the World Meteorological Day is observed with a different theme every year, the WMO said that the theme for 2022 is early warning and early action. Today, we have with us one of the young and eminent scientists in this field, Dr. M.G. Manoj from CUSAT, who will talk about the early warning and early action for disaster risk reduction. I'm happy to welcome Dr. Manoj, and I would like to introduce him about his career. He had his PhD in Atmospheric and Space Science from IITM University of Pune, and had his Master's in Meteorology from CUSAT itself, and BSc in Physics from Kannur University. And presently he is working as scientist in CUSAT. He was former research scientist in the same organization. And formerly, he was postdoctoral research associate in University of Maryland, USA. And he also served as a project scientist in Indian Institute of Tropical Meteorology, Pune. And before that, he was a scientific associate in the same institute. And he was awardee of Junior Research Fellowship during 2005 and 2006. And his area of interest is tropical meteorology, monsoon dynamics and thermodynamics, remote sensing, aerosol and cloud physics, air pollution and climate change, etc. And he has vast teaching experience also. He is having more than 40 publications into his credit, and large number of students are doing PG and PhD thesis under him. And he has undergone large number of professional training in this field, and most importantly, he had given more than 100 public awareness program, and all of you may be aware because he is a familiar face in the TV online programs, especially in news programs, in climate change discussions comes. And he is also a rank holder during his PG program. And he is also a member of various national and international bodies, including American Geophysical Union. With pleasure, I welcome you, Dr. Manoj. Over to you, please.
Thank you. A warm good morning to. Am I audible?
Yes.
Yes. Okay. Warm good morning to one and all. And at the outset, I would like to thank Dr. Srijit Kalpura for inviting me to deliver this talk. And I also thank him for the nice introduction. As he mentioned in the beginning, today's topic is early warning and early action for disaster risk reduction in association with the celebration of WMO Day. I would share my slide first. Is the slide visible?
Yeah, it's visible.
It's visible. Okay. So this is the contents of my talk today. I would just give you a brief idea about the Earth's climate, how the climate is controlled over a particular place, and some aspects of climate change. Then I would show you the projections of climate change and the impending disasters, and how to reduce this disaster risk associated with all the natural phenomena such as uh, extreme climate extremes. Okay, so this is, as I mentioned earlier, if you look at March, there is a very interesting aspect that you can see. On March 3rd, we have the World Wildlife Day. 21st March, we celebrate the World Forest Day. And 22nd March is the World Water Day. And today we have on 23rd, the World Meteorological Day. So if all these things go hand in hand or go together, then we can celebrate the International Day of Happiness. That is also on March 20th. So that means we take care of each and every component of the Earth as a system. And if that system, each of the system is cared or treated carefully, then we have a happy life ahead, of course. But we know the situation is somewhat different in the current scenario, especially in the backdrop of changing climate associated with global warming. So this year's theme is early warning and early action, and hydrometeorological and climate information for disaster risk reduction. And we know the WMO, World Meteorological Organization, it came into being on 23rd of 1950, 23rd March 1950, and since 1961, we have been celebrating this day with utmost care and also with a different theme for each year. And this year's theme is early warning and early action. And we, as Keralites, we know the importance of early warning and preparedness and the associated action for avoiding disaster risk. And if you want to see the Earth's climate, then we have to see it as a holistic system or an integrated system having different components. And there are processes in each of these the spheres, just like I would say, the atmosphere, the hydrosphere, cryosphere, lithosphere, and biosphere. If all these spheres act properly, and also interaction is also important. So the action and the interaction, they control the Earth's climate, and it makes Earth inhabitable planet. So if you see the Earth's radiation budget, you all may be knowing, it's actually a solar-powered system wherein the energy comes from energy for all the atmospheric and oceanic processes in the Earth's atmosphere is derived from the solar energy. And once it enters the Earth's atmosphere, some part is reflected. Say, for example, some 30% is reflected by the atmosphere, and rest 70% is incident upon the Earth's surface and the rest of the atmosphere. And this is coming in the form of a shortwave radiation, and the Earth re-radiates some amount of energy, say, for example, something like 59% of the incoming energy into space as long wave radiation. So this long wave radiation, they are infrared, coming under the infrared band, and they have a less energy compared to the incoming shortwave radiation. And during the terrestrial transmission, a part of this energy is being trapped by the so-called greenhouse gases, such as water vapor, carbon dioxide, nitrous oxide, surface ozone, CFCs, etc. These CFCs, if they are not there, let us imagine what would happen. Just look at this figure. Say, the Earth is continuously radiating energy into the atmosphere, and if you consider this as the outer circle as the top of the atmosphere, then we can say that an area of pi r square with r as the same radius of Earth is being intercepted by the Earth's atmosphere. So this amount of energy is being transmitted to the Earth's surface, and Earth re-radiates them back into space. So if you look at a long-term perspective, there is an equilibrium between the incoming energy and the outgoing energy, from which I can derive the average surface temperature of Earth from this equation. This is a very simple equation, a zero order model, and from this one I can say that the S is the solar constant, that is the amount of solar radiation incident perpendicular to this area, and it is the amount of radiation received at a unit area perpendicular at this one at a unit time. So that is what is known as a solar constant, and alpha is nothing but the albedo or the reflectivity that is coming radiating into the reflected component. Then 1 minus alpha into S is what is totally received by the Earth system. Then according to the Stephen Boltzmann law, we can calculate the average surface temperature of Earth as Earth from this formula, that is S into 1 minus alpha divided by 4 sigma whole power 1 over 4. Then if I theoretically estimate this T, then that T corresponds to something like a minus 18 degrees Celsius. Of course, we know that the average surface temperature observed with all the modern instruments over the Earth is around plus 15 degrees Celsius. In fact, this calculation gives us some value, something like minus 18 degree. So there is a huge difference between plus 15 degree and minus 18 degrees Celsius, that is 33 degrees Celsius, which is nothing but the greenhouse effect that I have not considered in this simple calculation or simple model. So this gives us a very valuable information that if or had there been no greenhouse gases, then the Earth's surface would have frozen to minus 18 degrees Celsius, wherein life would not have been possible. So thanks to this greenhouse gas, the 33 degrees Celsius additional warming, we are able to sustain, or we are able to make a living on this beautiful planet. Okay. But the question now is, then why are we concerned more about global warming or greenhouse gases? The answer is greenhouse gases are required to an optimal value or optimum value, beyond which, if they are increasing, then the average surface temperature would increase. And we know from the pre-industrial era to the current scenario in 2021, when the IPCC, that is the largest body, authoritative body under the UN, which had made an estimation that compared to the pre-industrial levels, the Earth's average temperature has risen by 1.1 degrees Celsius. Though it is a seemingly less or a very less number, it is nothing but the averaged surface temperature. That means at some places, the temperature would have crossed 1.1 degrees Celsius. So now it is close to 16 degrees Celsius. Instead of our 15 degrees Celsius, it is plus 16 degrees Celsius. And this 1 degree, additional 1 degree, can make a huge difference. Let us see it enough. What are the consequences after a couple of slides. Then, with regard to the unprecedented change in the greenhouse gases, there are certain climate change projections by the end of the century, that is by the end of 2100 or this century. What would be the average or the expected surface temperature, and what are the impending disasters associated with this increase or very huge or a huge amount of energy that is getting trapped in the Earth atmosphere system. And we know, if you see the average surface temperature of Earth, it has remained, or it had remained somewhere between this 0.2 plus 0.2 and minus 0.2 degrees Celsius on an average in the last centennium. And during the last 1 or 2 centuries, you can see there is a sharp shooting of this abnormal or the anomaly of temperature, average surface temperature, to almost 1 degree Celsius. And concurrent with this data, if you look at the greenhouse gas, especially the CO2 as a representative of GHGs, then you can see that the as this temperature increase happens in association with the unprecedented increase in the greenhouse gas concentration. And I would say, I don't know whether I missed that slide. Currently, the average CO2 concentration is nearing around 420 parts per million. And in the pre-industrial level, it was something like 280 parts per million. So a doubling of CO2 means 560 ppm. That means now we are 420 and we are just nearing close to that one, and we don't know what will happen. And that is the projection that the IPCC has given, which I will show in the next slides. And of course, when this is for the students, those who may be having some ambiguity between climate change and climate variability, what does it mean? If you see something like this sort of a graph, then look at carefully, this graph is actually composed of these short-term fluctuations plus a hidden long-term trend. So I can say this trend plus this short-term fluctuations give rise to this observed temperature. And we see that this up and downs, even if it goes in a particular year up, suppose if it is surface temperature, then in the next couple of years it will come down to normal. So we are not much worried, but we are mostly worried about this hidden trend. That means it is an irreversible change. It will not go back to its state. So as a result, what happens? The probability distribution functions of the probability distribution functions can also change. And if this is the probability of, say, for example, the normal distribution of average temperature, then there are different scenarios ahead of us. That means either the shape is preserved, but only the mean is shifted. And in that case, we can have more hot extremes. Or in this case, this is another scenario wherein you can only the amplitude is here, the amplitude is not changing, here the amplitude is changing, but the standard deviation is increasing on both sides, so that we can have more cold extremes and more hot extremes. Sometimes both can happen. So we, at each place, a combination of these factors is visible throughout the last century, and this is observed not only in temperature but all the meteorological parameters that we expect. And in the famous paper by Goswami et al. In 2006 science paper, they had revealed that the average rainfall over the daily average rainfall over the central Indian region for different categories. This thin line is for the moderate rains, and this thick line is for heavy rain, and this graph particularly is for the extremely heavy rain. You can see that the moderately raining days are decreasing or showing a decreasing trend, but the heavy rainfall and the extremely heavy rainfall are on an increasing trend. That means the average is not changing much, because this decreasing effect is partly offset by the increasing trend. And that's why we don't see any major shift in the seasonal rainfall, but we see the distribution pattern in a quiet or rapidly changing and alarming situation. That means moderate raining days are decreasing and extremely raining days are increasing. That can create havoc in various not only over India, this is true for most of the other places where monsoon is happening. So such changes have to be expected. Now, when we talk about the sensitive climate, it has got certain sensitivity, and you see, if I give you a rubber band, something like that, our natural tendency is to stretch it. And once we release the force or the strain, it will come back to its original state. So in this normal range, if I take this as the strain and this is a shear or the delta L, that's a change in the length of this rubber band, then for a normal condition, the stress is directly proportional to, or the strain is directly proportional to the strain so that it obeys the Hooke's law. But see, if you see this one here, if you exert much force on the system, then there's a deformation. That means it is somewhat changing its nature, and beyond this point, it will deform permanently. And beyond this point, see what happens, it will never come back to its original position. And if you still exert more force on the rubber band, then it will break. So same is the case with the climate system. We can have certain strains or some actions, but to a certain extent. Beyond that one, it will reach a point known as the point of no return. So this sort of a PNR should be avoided for a resilient climate. This is the lesson that we have to learn on this occasion. And we know when we talk about the climate change, these are the different sectors that contribute to the anthropogenic warming, where you can see electricity generation, heating is the largest single factor, around 44% contributing to the greenhouse gases. Yeah, this is the slide I wanted to show you before. You see here now, if you see from 1960 onwards, it is on a rapidly increasing side with the annual cycle of this one, and now it is nearing around 420 parts per million observed at Mauna Loa in the Pacific. So what could be the state of future climate? Whether it is, we don't know, but mostly it is hotter, drier, and wetter. That is the irony in this fact. That means we have to face a future where some place of the world is hotter and drier, and at the same time, the other part of the world is becoming wetter in terms of floods or severe events. So such a ironical state is what we see. This is not a fiction, but what we see in reality. So it highlights that without urgent action to cut emissions, the trend of increasing temperatures and the frequency and intensity of extreme events will accelerate, because we know, according to the Clausius-Clapeyron equation, for 1 degree Celsius temperature change, it can hold almost 7% additional water vapor in the atmosphere. If water vapor is available, then those enhanced water vapor can lead to deeper clouds and heavy precipitation or extreme precipitation. In the IPCC 2007 report, they had shown during that time, it was different future scenarios, A2, A1, B, B1, you know that. Under different situation, future scenario, the IPCC had projected a temperature change of 3.5 to 4 degrees Celsius by the end of 21 century. Different scenarios. And we have the AR6, that is the Assessment Report 6 on 9th of August 2021, which also I will show here. That is the IPCC AR6 released, this is the hot extreme, and this is a world map. This is Canada, North America, and South America. This is Africa, Europe, Asia, and the Australian region. So each hexagon represents with 3 dots. That means the confidence level, whether it is high, medium, or low. If it is 3 dots, then it is high, and this color increase, this color pale pink color shows an increase of hot extremes. In the future, we have to all over the world you see pink. That means globally the surface temperature is going to increase. The Southeast Asia, this is the region where we are living, and that is also no exception to this one. And in terms of heavy precipitation, you see, there also, all these places in the future can expect increase of heavy precipitation. And you see, there is no decrease shown in this figure. And here it is show either low agreement or limited data. So we have to verify this one, but most of the world is going to shift to a new climate regime, wherein hot extremes and cold extremes or heavy precipitation events are going. And this is the figure for the agricultural and ecological drought. You see here also most of the places are going to face this critical situation of agricultural and ecological drought. And compared to the other conditions, that is the different scenarios or the RPC, here in this report use the shared socio-economic pathways, and there are different, at least 5 different types of pathways. That means how the future will look like depending upon our current action and the future action. Then it has estimated that the surface temperature under SSP3 and SSP5, the surface temperature on an average will go or rise beyond 3 degrees Celsius. And we are nowadays talking about the 1.5 degree limits. Almost all the climate summits, we are arguing that whether the limit will be crossed in the 2040s or whether we are going to a 2 degree Celsius increment regime. And here by 21st century, this is the most widely accepted challenge or the disaster that we have to face. And in the 1.1 degree Celsius itself, it's sometimes unbearable to live here. So just imagine what will happen in this one. And of course, here the changes are not linear. That means 1 degree Celsius increment from +1 to +2 and +2 to +3. The same 1 degree increment will not have the same linear impact, linear scale impact, but it will be rather highly complex and unimaginable. And here, this is with respect to Kerala, thanks to Dr. Abhilash, his project. Here, this is a pre-monsoon, annual, winter, and this is the increase in the maximum temperature for the pre-monsoon and the annual, and for the winter, this is a T-min, because T-min is mostly observed during the winter time, and the annual changes. Whatever, whether it is or irrespective of the maximum temperature or the minimum temperature, you see the color is the yellow to red. That means an increase. Nowhere you can see a decrease of temperature in the future. That means all over, in accordance with the global scenario, we are also experiencing a part of it, in addition to the local scale microclimate, which I will skip here because of for shortage of time. And the monsoon also shows different patterns. Some in northern Kerala increase, southern Kerala decrease, something like that. But we don't know. It will depend on the actual scenario. This is based on the projected scenario. And the increased cyclones frequency from 2017 Oki cyclone to the latest cyclone in which had just passed through or parallel to the Kerala coast on May 14th, 2021. That is the Taute cyclone. They are all coming near. Until now, we were almost thinking that Kerala is a cyclone-free zone, but that concept has to be changed. Anytime we are also vulnerable to this impact of cyclones, and the increase in frequency and intensity of cyclones, especially in the Arabian Sea, is also a greater concern for Kerala. Then let us just see, after this, I will go to the disaster risk reduction part. Why we are so particular about this 1.5 degree limit and 2 degree limit? Because we know in a day itself, temperature changes by more than 15 degrees Celsius to 20 degrees Celsius from the morning to the afternoon hours. So there is a wide range of temperature. But why are we talking about this 0.5 particularly? I will just give some glance on this one. First thing is that the global warming is about average temperatures. I talked in the initial, at the beginning itself, that it is an average temperature. That means some places, then there is a fact that average temperature rise, spikes and heat ups will go much higher than 1.5 degrees Celsius. Some places have already crossed this limit of 1.5 degrees Celsius, especially the Arctic melting rate. If Arctic is melting more than what we at a rate that we expected, then there is accelerated melt of glaciers, and this glacier melting will lead to sea level rise in addition to the thermal expansion. So we can have increased storm surges, sea level rise, and coastal erosion, etc. And we know we have more than 6,000 kilometers of coastal areas for India, and the main cities are located on the banks of these shores. So we have to be very careful about this sea level rise, especially the Indian Ocean and the Arabian Sea. It is almost heating at almost 1.8 times. I would say 2 times compared to the global average. So the impact will be unimaginable. Then, if from a 1.5 degrees Celsius to a 2 degrees Celsius, what happens? Already, I will just read it out. Already, the world has hit to around 1 degree Celsius above the pre-industrial level. Each of the last 4 decades was hotter than any decade since 1850. That means the current 4 decades, they were the hottest one after another. And for every increment of global warming, changes in extremes become larger. That is the most important point. Changes in extremes become larger at a non-linear scale. Warmer atmosphere holds more moisture, that we know. Half a degree means much more extreme weather, and it can be more often, more intense, or extended in duration. So the increase in frequency, duration, and the severity can lead to almost 1.7 million more people experience the severe heat waves at least every 5 years. So sea level rise increase, another 10 centimeters is expected, decades, and an extreme heat wave that occurred once per decade in a climate without human influence would happen 4.1 times at a decade at a 1.5 degrees Celsius warming. And it will become 5.6 times at 2 degrees Celsius. You see, here the difference is only 1.5 to 2 degrees Celsius. But the impact is 4.1 to 5.6 times. And if the temperature increases to 4 degrees Celsius, the heat wave would occur 9.4 times. That means almost 10 times compared to the pre-industrial levels. Then regarding Celsius, there is good chance that we can prevent most of the Greenland and West Antarctica ice sheet from collapsing or melting. But warming of 1.5 degrees Celsius would destroy at least 70% of the corals. But at 2 degrees Celsius, more than 99% would be lost. See, from 70 to almost 99% for a 0.5 degrees Celsius change. That would destroy fish habitats and communities that rely on reefs for their food and livelihoods. Then food, forest, and diseases. Warming of 2 degrees Celsius versus 1.5 degrees Celsius would also increase the impact on food production. Global fishery catches could decline by another 1.5 million tons. A warmer world could see the mosquitoes that carry diseases such as malaria and dengue fever expand across the wider range. But 2 degrees Celsius would also see a bigger share of insects and animals lose most of their habitat range compared with the 1.5 degrees Celsius. And an increase in the risk of forest fires, that is another risk to not only wildlife, but for human-wildlife conflict also. Then rainforest system collapse, release CO2 into the atmosphere rather than storing it. Or warming Arctic permafrost could cause long frozen biomass to decompose, releasing vast amount of carbon emission. Not only carbon emissions, such a type of dormant type of bacteria existing far beyond several centennials would also be released in the atmosphere or into the Earth system. And biodiversity loss, that would be enormously depleted. Food security would drop, and extreme weather could exceed most urban infrastructure's capacity to cope. In this scenario, you see the 2018 and 19 floods that occurred in Kerala, and we are witness to this one. And we know what are the consequences, socio-economic impact, and valuable lives were lost. And what to say, the end-to-end floods, 2018, 2019, and in 2020, some part of northern Kerala, and in 2021, the central Kerala. So this is now becoming a story without any news value. And there is a prominent change that we see during the monsoon time. Generally, the cumulonimbus clouds are not seen during the monsoon times, but nowadays very deep clouds are forming in and around the Kerala coast, which can create cloud-based type of events and even lightning during monsoon times. So this is the 2019 figure. This is the climatology. You see the anomaly here. It is increasing like anything. And especially if you look at the flood that occurred in 2018, there's a shift in the LLJ pattern due to the influence of the West Pacific typhoons. That means the West Pacific typhoons can act like a system that can draw in the or change or shift the pattern of LLJ, which just passed over Kerala region and produced this torrential rain or the historic flood waves. So certain atmospheric waves were also excited during this time, which had its role in the distribution of energy in the atmosphere. So the system entirely got changed, and we had to face the severe flood during that time. And certain events like the heat burst during monsoon is also experienced. KFRI is also a part of the study during the 2015 monsoon, June time, when the monsoon was very weak. We had heat burst type of events, and along the coast overnight, the trees were burnt, and this was due to the presence of the thunderstorm events, as evident from like a microbase type of thing. Heat burst events had occurred, which was captured by these automatic weather stations installed at Thrissur. And now, with this background, I would just have a glance for the disaster preparedness, because we are sure that disasters are on an increasing trend, and we have to somehow avoid the risk. Then let's see this formula. Disaster can be split up into a hazard, a physical event plus vulnerability. So a physical event, if it doesn't claim or doesn't destroy much of the property, then we can reduce this disaster to a hazard only, and we can save valuable lives. So this our aim is to reduce the vulnerability, so that the impact of disaster can be reduced. And for that condition, and we know during this time, especially during the pandemic time, and that pandemic itself is having certain roots in the on climate change, increasing temperature, varying humidity profiles, etc. We are nowadays experiencing not only a single hazard. That is the main point that we have to face, or we have to see. Certain events are occurring simultaneously, and we call it as a compounding event, or multiple hazards. Sometimes they are compound events. That means they occur together. For example, during the COVID time, we had flood. So for the disaster management point of view, we had to be prepared with the shelters for the COVID affected people, the non-affected people, and highly vulnerable people likewise. So it actually increases the risk of these hazards. And from there, we have to think of linking early warning with the early action. That means we have to close the gap for stronger resilience. Now talking about the early warning system. That is, most of the warning is given in the form of a forecast-based early action and early warning system. So they are integral components of disaster resilience. They have the potential to reinforce one another and enhance the effectiveness for greater risk reduction, managed response. In this situation or scenario, we have to think of the 2015 Sendai framework for disaster risk reduction. That was a global initiative for, we call it as the Sendai framework targets, and they link to the sustainable development goals. There are certain sustainable development indicator system and custom and regional targets and indicators. So this is the Sendai, the front page of the UN General Assembly. They gave certain indicators and terminology related to DRR. One is a disaster vulnerability, exposure, prevention, mitigation, resilience, hazard, underlying disaster risk drivers, disaster risk, etc. Each one is well defined and they are interconnected. And they put forth at least 7 global targets. So out of the target A, target B, etc., target G, you see the target G is basically for substantially increase the availability of and access to multi-hazard early warning systems and disaster risk information and assessment to the people by 2030. So all the nations are trying their level best to achieve this goal, Sendai framework target G. And for that targets, there are certain priorities for DRR under the Sendai framework. One is the understanding of disaster risk, then strengthening disaster risk governance to manage disaster risk, investing in disaster risk reduction for resilience. This is really important. We have to invest for disaster risk reduction, not in the post-disaster phase, but in the pre-disaster phase itself. We have to invest. That means a stitch in time saves 9. This is the idea basically put forth. And enhancing disaster preparedness for effective response and to build back better in recovery, rehabilitation, and reconstruction. Those who don't know build back better, this is the definition. Building back better is a strategy aimed at reducing the risk to the people of nations and communities in the wake of future disasters and shocks. So the BBB approach integrates disaster risk reduction measures into the restoration of physical infrastructure, social systems and shelter, and the revitalization of livelihoods and economies and the environment. So it is a holistic approach for the revoking or the post-disaster restoration. And several countries have come up with certain outcome areas like the disaster management plan. So one is professionalizing the disaster management system for rural risk reduction, then urban risk reduction. Rural is complete, or urban is completely different from the rural risk reduction. And preparedness and response, maintaining DRR and climate change adaptation, then community level climate change adaptation. This is really important. From the point of DRR, we have, earlier we were thinking that community level climate change adaptation is much more. Now we have slightly refined this idea. That means we are now using the concept of ecosystem based adaptation. That means the ecology or the environment is also taken into consideration along with our needs. Then early warning and early action, the steps to make it happen. These are the steps. One is I won't go to the early warning system definition and all. We all know it is an integrated system of hazard monitoring, forecast, and prediction for avoiding this risk. So, what is an effective early warning system? That an effective early warning system should be end-to-end. That means fully covered. And second one is it should be people-centered. And it should consider the nature of multiple hazards occurring simultaneously, cascading, or cumulative over time. So whom it should reach, we will see. These are the components of an early warning system. That is risk knowledge. What are the risks associated with a particular hazard? That we should know. Then monitor and warning the system. We should monitor that one and we should give early warning. Then according to the early warning system, the community should be, or the people should be prepared. Not only the people, the government, the disaster managers should be prepared, and they should increase the response capacities and make people aware of what are the steps to be undertaken during such emergency situations. Then warning, dissemination, and communication. Proper warning in terms of local language. Their colloquial language, warning should be there. Not in technical jargons, but in terms of very language and easily understandable by all the people. All the people means, you know, as a society, we have differently abled people also. So they should also understand the gravity of the situation. So such type of communication system should be developed. Then first thing is the risk knowledge. An effective early warning system considers the dynamic nature of hazards, vulnerabilities, and exposure within a specific location. So for this one, we have to review the data, make a seasonal calendar of the events, generally the climatology and community mapping, spatial mapping we have to make. We have to produce the hazard risk vulnerability map, capacity and resource map, and there are certain metrics or indicators for distinguishing from one another. Such type of actions are required at the root level. Then, when doing risk analysis, it is critical to look at the intersection of the effects of this hazard with any long-term change processes related to climate change, because a short-term action can have a long-term impact. So we have to see what are the long-term impacts. Then accordingly, we have to plan much early and arrive at the very optimum solution. Second one is monitoring and warning services. So here certain questions are to be considered. What are the, or which are the best forecasts that can be used? For example, for as far as the Indian Meteorological Department is concerned, they have a suite of models. Each model is different, and we don't know as a common man, we don't know, even if the output is produced to you at free of cost, you don't know which one to rely upon, and our decision also will be faulty depending upon the model that we use. So which are the indicators that should be monitored? That also we have to consider. Are the right indicators of the hazard being monitored? Then should various indicators be monitored in parallel to be able to issue a warning? So such type of a comprehensive analysis should be done, and we have to choose the best among them. For this one, especially the numerical models are used, especially hydrometeorological purpose. We use the this. I think everybody knows it. Earth is composed of or divided into certain cubes in the, or divided into latitude, longitude, and height levels. Then under each such cube, we see what is the input mass flux, incoming, outgoing, energy incoming, outgoing, etc. So thus, if you see a grid, this is the structure, and for each of this grid, we have a set of, this is a three-dimensional climate model. We have a set of differential equations that govern the flow of energy, mass, and momentum into this one. At least 7 variables are there. We have to solve them simultaneously at each of those millions of grids, because the higher the resolution, that grid number will increase exponentially, and you have to solve them within no time. So we have to rely on supercomputers for solving those equations. And even if we use the best supercomputing facility, then still there will be numerical errors or numerical instabilities which need to be reduced for a better and accurate result of the future state of the atmosphere. These are the sets of equations. I won't go into much into details. And this is the fundamental idea of models. That is the rate of change of any particular variable is here. This is the time rate of change of a particular variable. For example, temperature. So it will be dt by dt, where T, capital T, is the temperature. So the change of temperature over a particular time period is given by the new value minus the old value divided by the interval. Then likewise for each grid, we calculate the change of the future state of atmosphere, and then we give a forecast for this one. So what happens actually, the prediction technique using this equation of change is then to take many small steps and recalculate or update the new principle at each step. This technique is known as iteration, and it is the approach taken for computer forecasting of weather, climate, economics, etc. Not only for weather, but for other geophysical events and even financing also, we use such type of models. And we use this on a spherical, in the spherical coordinate, because Earth is spherical in nature. So it is better we use the spherical harmonics of those equations But still, as far as the early warning is concerned, there are still a lot of challenges of this computer-based forecast system. One thing is that the non-linearity of the problem. It is not that suppose the temperature of a particular location we want to forecast, then that change is attributed to several causative factors, not a single one. So the non-linearity comes into picture. That is the first problem. Then simultaneous solving of billions of nonlinear equations. Then to save time, we have to truncate the series because we do it numerically. Then numerically, we have to truncate the series at certain after 2-3 major major terms we retain and the rest of the terms we avoid. So that avoiding those small scale terms in the long run will lead to instabilities or errors. Then the third one is the limitation of theoretical understanding of the physical process. We still don't know how a deep convection is forming. We have certain ideas, but under different shearing environment, how a deep convection can transfer or how a moderate convection can suddenly jump into a deep convection is not known. So such a phenomenon is also not accurately represented in the model. Then lack of high resolution ground observation is another drawback, because we have in Kerala especially, we have observations at a very coarse resolution, and in between whatever happening processes, subgrid scale processes, they are missing. That also leads to errors. Then inherent limitation of the prediction in the tropics, that is yet another big problem. Compared to the extratropical and the polar region, the tropical region is dominated by the impact of barotropic instability and the more type of the upper hand of temperature, and the thermodynamics comes into play, which is still poorly known phenomena because of the non-linearity. Then even if we are done with all these above causes, then in the warming environment, that climate change also affects our reliability. So these are the real issues that we face in the current scenario. Then to improve our weather forecasting skills, we have to, here you see the limit, the lack of high resolution ground observations. Over the land area, we have ample observations, but over the ocean, we have very, very coarse resolution observation. So when satellites came into picture, we could improve this. You can see this is a very important paper in the 1980s, where huge updates due to satellite radiance data. This is known as data assimilation. By assimilating this data, we could make much more progress during the recent years. And data assimilation is from the observations, we do certain analysis, and this analysis is going into the model and give a forecast. So in between, what happens, you have to, I will show here, with the use of wind profilers and ensemble Kalman filters, they are used for the 4-dimensional data assimilation, then we can improve the accuracy of the forecast. See here, if you can see the anomaly correlation of 500 HP geopotential forecast, this upper line is for the, this is a day 3 forecast, day 5 and day 7. And the thinner line, the bottom part is for the southern hemisphere. You see, with the improvement of data, with the addition of data assimilation, the accuracy level can be increased over the period, especially in the 2000, this decade. And you can see that now it is almost one and the same. But in the pre-satellite era, there were this much discrepancy were there. So this is a greater impact of satellite data assimilation into this one. Similarly, the European Center for Medium Range Weather Forecasting, their RMS error compared to other global centers you see this red line, the RMS error for the day 3 and day 5 forecast, the RMS error is decreasing as a result of the data assimilation. So this is with respect to hydrometeorological only. There are other geophysical phenomena which I have not touched upon here, or compounding events are there. For those ones, we need a better prediction system. Now, as far as the DRR is concerned, now we have to be prepared, and response capacity we have to increase. So, because our time is 1 hour, I am almost going to close it. I will just skip these details. The preparedness and response capacity we have to increase. See, for example, here, early action between a forecast and a predicted event that can have a better time for disaster response and recovery. So we have to increase the lead time of prediction also. Then warning dissemination and communication, as I told earlier, different methods are available, especially with the use of ICTs, in information and communication technology. Our forecast dissemination is also increasing, but still there are a lot of gaps, especially fishermen going into far deep sea. Sometimes they are not able to get the proper warning well in advance, because they start 2-3 weeks ahead of the, suppose in the case of a cyclone or something like that, they go much beyond that. So there should be proper system for long range communication under cloudy conditions. So such things are there, and certain public awareness programs like the flash mob type of things also create public awareness. Then this is the leveraging of ICT, that is the information communication technology, to better collaborate with wider groups of stakeholders through protecting citizens from natural disasters to ICT-based disaster warning and management technologies, establishing networks with all the mobile phone companies and use those for speedy dissemination of early warning information to the community, promoting SMS-based disaster warning system targeted to the population likely to be affected. Then utilizing the geographical information system-based systems to monitor flood, cyclone shelters, and ensure a equitable distribution of relief goods with a special focus on the hazard to reach areas. Then we have to go to the community early warning system, because there are certain privileged communities who are beyond the access of regular communication systems, and such communities, for example, the tribal communities, Adivasis, etc., they should be taken care of by special efforts, like maps rather than words. Some maps, how to read from the maps, how to read from the say, for example, green alert, orange alert, red alert, what are the actions that we have to take. Likewise, it should be conveyed properly to those communities. And preparedness for effective response, that we have to it refers to the measures and actions taken by a national society to prepare for, respond to, and recover from and reduce the effects of disaster and crisis. We have to increase this preparedness for effective, PER should be increased. And I would, with this slide, I will just stop. Here, one important thing is what is forecast-based financing. That is one important thing. A mechanism that uses climate and weather forecast and risk analysis to enable the timely disbursement of funds to implement early action before a potential disaster happens. See, in the post-disaster phase, spending much more money, and in the pre-disaster case, spending much more money for preparedness can have huge difference. So the forecast-based financing is the better idea that we can promote during this decade, and it can have a very huge positive impact on our this one. Here you see an example of a forecast-based financing. This lady, I am so grateful to the cash. I bought fodder for my cows and could evacuate them. Without the cash, I would have had to sell them, but they are very good cows. They deliver good milk and are very healthy. So such type of models can be adopted for the vulnerable categories. With this one, I would thank all the participants for listening patiently to my talk. And I once again thank Kerala Forest Research Institute for inviting me to deliver this talk. Thank you.